Hello, and welcome to another SVSU Math and Physics Resource Center video. My name is Matt, and I will be your tutor for today. In this video, we are going to go over a problem dealing with the rotational inertia, center of mass, and period of a physical pendulum. In the figure, the pendulum consists of a uniform disk with radius r equals 10.0 centimeters and mass 500 grams, attached to a uniform rod with length L equals 500 millimeters and mass 270 grams. A. Calculate the rotational inertia of the pendulum about the pivot point. B. What is the distance between the pivot point and the center of mass of the pendulum? And C. Calculate the period of oscillation. Okay, so the units in this problem are just all over the place. So the first thing I'm going to do is I'm going to convert all of our units to standard units. So R, I'm going to convert to meters, so we'll have 0.1 meters. The mass of the disk, I'm going to say m of d, is going to be in kilograms, so I'm going to change that to 0.5 kilograms. The length of the rod is 500 millimeters or 0.5 meters. And our mass of the rod, m sub r, is 270 grams or 0.27 kilograms. Now for part A, they asked us to calculate the rotational inertia of the pendulum, and we're going to have to do that in two parts here. We're going to do first the rod, and then we're going to do the disk. And we're going to be using the integral definition, integral of r squared dm is equal to I. And we're going to be using also the parallel axis theorem. I total equals I center of mass plus mh squared, where h is the distance from the center of mass to the pivot point. For the rod, what we're going to have to do is integrate over the mass distribution from the pivot point here to the end of the rod. So in this equation here, r I'm just going to call x because this is just a linear distribution, and dm is going to be defined as lambda dx, where lambda is the linear mass density of the rod, and since this is a uniform rod, we can say lambda is equal to mass of the rod divided by the length of the rod. So if we put all of that together into our integral, we get the integral from 0 to L of x squared times m sub r over L dx. And we can pull this m sub r over L out and then integrate the x squared dx, which will give us m sub r over L times 1/3 x cubed from 0 to L. And then if we plug in L and 0, we're going to end up at the end with 1/3 mr L squared. Now the disk is going to be a little more complicated. What we're going to have to do is find the rotational inertia of the center of mass of this disk here, and then use parallel axis theorem to move the pivot point to its correct position. So in order to do that, first we're going to define a few things. This is going to be an area distribution of mass, so our integral is going to have to be a double integral. So I of the disk is equal to the double integral of r squared dm, and dm in this case is going to be defined as sigma dA, where sigma is our area mass density. So this is a uniform disk, so we know sigma is going to be equal to the mass of the disk divided by the area of the disk, or pi r squared, where big R is the radius of the disk. Since our disk is a circular mass distribution, it'll be useful to write dA in terms of polar coordinates. So dm is actually going to be m sub d divided by pi big R squared times r dr d phi. So if we put this all together, the rotational inertia of the disk should be the double integral of r squared times m sub d over pi big R squared r dr d phi, with our bounds on r going from 0 to big R and our bounds on phi going from 0 to 2 pi. Now, if we integrate the with respect to r, we're going to end up with m sub d pi r squared, integral from 0 to 2 pi. Integrating r cubed with respect to r gets us 1/4 r to the 4th from 0 to big R d phi. Now, what we can do is plug in our big R and 0 to this, so we end up with m sub d over pi big R squared, integral from 0 to 2 pi of 1/4 big R to the 4th d phi. And then since this has no phi dependence, we can pull that out as well. And we're going to end up with, if we put all of this together for now, we're going to get 1/4 m sub d r squared over pi times the integral from 0 to 2 pi of d phi. And integrating that, finally, integral from 0 to 2 pi of d phi is just going to be 2 pi. So we're going to end up with 1/2 mass of the disk, radius of the disk squared. Now this is just the rotational inertia of the disk at its center of mass. If we want the rotational inertia of the disk at this pivot point here, then what we're going to have to do is use the parallel axis theorem here, where h is the distance from the center of mass to the pivot point. In this case, it's going to be L plus R. So if we set that up, we're going to get I for the disk is equal to the I center of mass for the disk, the 1/2 m sub d big R squared, plus the mass of the disk times the length of the rod plus the radius of the disk, all squared. Now for the total inertia of the pendulum, we just have to add the inertias from the two pieces that we have. The I for the rod plus the I for the disk. And the I for the rod, if you remember, was 1/3 m sub r L squared. And then I for the disk, of course, right there is 1/2 mass of the disk times radius of the disk squared plus mass of the disk times length of the rod plus radius of the disk squared. Now, if we plug in all of our known values, we end up with I for the pendulum as 0.205 kilogram meters squared. So for part B, what we need to do is find the center of mass of the full pendulum. So nicely enough, we can treat the disc and the rod as two separate point masses centered at their center of mass along the axis that runs through the pendulum. Now, I'm going to define this point here, the pivot point, as x equals 0, and we're going to use the center of mass equation. So x center of mass is equal to m1 x1 plus m2 x2 plus dot 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 divided by m1 plus m2 plus and so on. So if we want to plug this in, we've got the center of mass of our pendulum is going to be at mass of the rod times x of the rod, and that's going to be at the center of the rod because it's a uniform rod, so that's going to be at L over 2, plus mass of the disc multiplied by x of the disc, which is going to be the length of the rod plus the radius of the disc, so L plus big R, divided by m sub r plus m sub d. And if we plug all of our values in, we still know all of these, we end up with the center of mass of the pendulum being 0.477 meters away from the pivot, or 47.7 centimeters. Finally, for part C, we need to find the period of oscillation for this pendulum. So the equation for period of oscillation for a physical pendulum is the period equals 2 pi times the square root of the rotational inertia of the pendulum divided by the total mass of the pendulum times acceleration due to gravity times h, which is the distance from the pivot point to the center of mass of the pendulum. Now, from part A, we know that I is equal to 0.205 kilogram meters squared, and that from part B, we know that H is 0.477 meters. And our total mass is going to be the sum of the 0.5 kilograms and the 0.27 kilograms of the two pieces. So that's going to be 0.77 kilograms, and gravity is of course going to be 9.81 meters per second squared. So if we plug all of this in, we get T, the period of oscillation for the physical pendulum, is going to be roughly 1.5 seconds. Okay, that's it for this problem. I hope it was helpful. Thank you for watching, and we will see you again in another video. Bye!